Bingo, Monday, 1 o'clock rock. You know what that means, research in Manoa every Monday, 1 o'clock. And today a special guest, Patricia Fryer with HIGP, a real scientist. And we're gonna talk about Mariana Trench National Marine Monument, the very inestimable Mariana Trench National Marine Monument. Welcome to the show, Patricia.
Oh, thank you so much, Jay. It's always a pleasure.
We're calling this show Subduction Can Be a Beautiful Thing.
Ah, indeed. Quite beautiful when you're down there looking at it. Not so great when it creates earthquakes, but we'll talk about that.
Okay. Let me ask some preliminary things before I get into, your science. And that is, there's a bill pending in the state legislature. I think it's HB 1700.
Yeah.
And that bill would take research funds away, state research funds away.
That's true. That's what it seems like. And if so, I don't know what the research units are going to be able to do. Maybe about half of the people who work in the unit that I work in are paid for essentially by the other half of the people that work there. And the legislators that are supporting the bill are thinking that we're going to be able to make up the other half of what's needed from federal funds. Well, one thing is I am not permitted by the National Science Foundation to ask for more than 2 months of salary. That's it. Other people have a similar sort of restriction. But, the folks that are paying for the people that aren't getting paid by the state right now aren't going to be able to pay them.
Yeah.
And those people are the support for the research that they do. And so if those people can't get paid and have to leave and do other jobs, then the primary researcher can't do the job and has to give the money back to the federal government. So that's the end of it. And where are they going to go? They're going to have to leave Hawaii, and that means that our grad students who are local won't be able to do any research at the university. And what scares me is, we're gonna have this group of young people coming up with an interest in science of all kinds who are gonna have to go to the mainland for their graduate school and maybe even for their undergraduate school. And they're not gonna come back. They're gonna find jobs there. They wouldn't be able to find jobs at UH. So, we have this terrible drain of intelligent kids leaving the islands, and that's just tragic.
Yeah, and the other tragedy is that a lot of the science at SOWest, if not most of it, is specific to Hawaii. Hawaii's the best place for it.
Well, absolutely. I mean, the unit that I work with advises the state on everything from, volcanic hazards, earthquakes. My husband is the tsunami guy. He's Gerard Fryer, the person you see on TV, when there's a tsunami alert. And he actually left the university to work at the Pacific Tsunami Warning Center. But, the reason he got interested in tsunamis was because he was doing seismological research here in Hawaii. And all of that expertise is in danger of leaving. What are we going to do?
Well, I guess the
I hope
bill
it doesn't go through.
Redirects the money to, so 45 million sticks in my
Yeah.
brain, redirects $45 million of research funds into maintenance, and which
We definitely need maintenance, yeah.
definitely
I
maintenance,
agree.
but not at the expense of doing the science.
Well, there has to be some mechanism by which the research can continue. And let's hope that that's eventually what's discovered within the ledge.
Yeah, I hope that's discovered soon. I mean, this is our university. We're part of it, it's part of us. It's a statement of, the direction of the state. It's a statement of the excellence of the state, and we really can't afford to lose it on any number of levels.
No, I'm with you on that.
Okay, well, let's talk about your science. First, what kind of a scientist are you, aside from being an excellent scientist?
Oh, thank you. Yes, of course. I am what's called a marine geologist. And it's the sort of thing that, when you're on an airplane and you sit down next to somebody, right? And you make conversation, hi, where are you going? Oh yeah, well, what do you do? I'm a marine geologist. Oh, you study dolphins? No, I study rocks from the seafloor and volcanoes.
Geology.
It's okay, people are nice. So but then we talk about things like subduction and volcanoes on the seafloor.
And they say
diving in
subduction
submarines.
can be a beautiful thing.
Ah, I wish. Sometimes.
Okay, so you study subduction.
I
And
do.
subduction means moving the plates back and forth.
That's right.
And that's important in our time, isn't it?
Wow, yeah, indeed. Subduction processes, like where I work, is in the Mariana region, which is out near Guam in the Western Pacific. And the Pacific plate is moving down beneath the edge of a big plate of crust and upper mantle that Guam and the rest of the Mariana Islands sit on. And as it does so, it doesn't move really fast all the time. It kind of gets stuck and builds up stress over long periods of time. And then when it moves, that's when you get huge earthquakes. So just like the Japan earthquake of 2011,
that was serious.
that was incredibly serious. And the more that we can learn about what physical processes are going on within that zone where the plates are contacting one another, the better able we are to understand what kinds of things are required for the Earth to slip like that in subduction zones.
Yeah, but so you figure out that this side's going down,
Right.
and this side's stable. Is this
Yeah.
this is the west side, and this is the east side?
Uh-huh.
Okay, and it's going down.
Oh, other way around.
Other way. Okay.
Okay, for the
So
Marianas.
the lower side
Yeah,
is the one coming in from the east,
correct.
and the upper side coming in from Asia.
Yeah,
Okay, and this side's pressing on that side, and
right.
it's slipping, and lots of friction.
Absolutely.
And so we need to know about the friction, where it's coming and how fast it's going, and
Right.
what makes it happen that way, and what the effects are. But if I know all of that, what do? I get down there and I say, wait, no, hold up, will you?
I wish, right? No, what we can do these days, and in fact, the Japanese have done this, and it's so cool. They have the ability with remotely operated vehicles, and these are robotic vehicles that can go down to the seafloor, to string sensors down right at the bottom of the trench in the Japan Trench. And these now can monitor what's going on in terms of movement of the overriding plate and the downgoing plate, and try to understand what sorts of things might precipitate a slip on these contact zones.
What do we think now? I mean, the things that precipitate.
Well, what we think now is very different from what we thought before the Japan earthquake. As I mentioned, my husband's a seismologist, and his group of friends, everybody who goes to the national meetings was talking about, we didn't expect that there could be a magnitude 9 in the Japan Trench. And there was. I mean, most.
Have we seen magnitude 9s before?
Now that is a good question, because the run-up, or the area covered by the tsunami from 2011 was a surprise to everybody, except that when people were going out into the field and mapping where the water had got to, they started finding these huge rock cairns. And these things were erected back in, I think it's 860 something. I can't remember the exact date. But these things said, don't build any closer to the ocean than here. And over the ensuing hundreds of years, people just kind of forgot about this. That's the problem with us. We live such a short life that we tend to forget about these things. But we still cannot predict an earthquake. What we can do is to learn more afterward exactly what happened, what kinds of things, for instance, on the surface of the seafloor, what caused the tsunami to be so big, and Well, if Gerard were here, he could go on and on and on, but I know a little bit about it, and that is that there were submarine landslides that enhanced the motion of the tsunami, that caused it in part to be so big and to move so rapidly toward Japan.
Rapidly, how rapid is rapid?
Oh, well, on the open ocean, a tsunami wave will travel at the speed of a jet plane, 500 miles an hour,
Wow.
roughly.
Wow.
So-
So that means that in a very few hours, it'll cross the whole Pacific.
Exactly, yeah.
Wow. So, so I'm thinking that if you learn everything you want to know about the subduction process and the sliding plates, that will enable you to anticipate and predict not only the timing of an earthquake within bounds, but also the force of the earthquake. You can tell. Am I right? You can tell.
No.
So
No,
what does
I'm
it help
sorry.
us predict?
No. What we're trying to learn about, well, the reason that we can't predict it is because there's no way that we're going to know everything about, the contact between one huge plate and another.
It's a data question.
It is
If you had sensors all over that plate, you would know. Maybe not.
Yeah, maybe not. The Earth is a fickle woman.
I'm going to change the title of the show.
Oh, whoops.
Subduction. Okay, so just really getting interesting. The other thing I get out of what you were saying is that maybe, just maybe, these processes are dynamic.
Oh, definitely.
And that the Earth is on a course somewhere, different than it was before.
Yeah, an interesting question. It does seem, and I'm getting out of my field here a little bit, but from what I have heard my husband saying is that...
You guys talk about this at dinner all the time, I know.
Well, no, not all the time, but, kind of when we first get home, blah, blah, blah. But he says that what they have seen in the early part of the 20th century was a lot of relatively large earthquakes. A really big one in Chile. You may not remember, but I remember the 1964 Alaska earthquake. So, that tsunami hit the islands. 1946, I wasn't here, but that was huge. But it was all in the earlier part of the century. And then more recently, after 2004 in Sumatra, they've been following on a lot of large earthquakes and resultant tsunamis. So is there a pattern? We don't.
Is there a pattern? Yeah.
We don't really understand the Earth well enough. We've only been studying this stuff, for less than 100 years.
Yeah. Well, you know what? It's interesting to me because the general view of things, the environment, the Earth environment, is that if you abuse it, it will bite you back.
Oh, yes. Definitely.
And I'm wondering, if humankind is abusing it now for at least 100 years, several hundred years, really, okay, we have climate change, we have a rise in temperature, all that.
Right.
We have acidification, and all the
Yes.
biological things that flow out of
Right.
that. But I wonder if there's a geological impact. Ooh, this is a hard one. A geological impact to climate change. Maybe could it be that we abuse the Earth in one way and it bites us back in a completely different way?
Well, that's an interesting question. We'll perhaps leave that for those of us who are more knowledgeable in that field.
Well-
but the Earth may also be helping us, human beings, figure out, ways to maybe curtail some of our more nefarious activities. Aha, I have a sample.
Wait.
Can I show you?
No.
No. Oh,
We're going to take a break.
Oh, we
And
are?
I don't even want them to know what the sample is until
Okay.
we come back from the break when they'll be surprised.
All right.
Cliffhanger.
Oh, boy.
We'll be right back.
Okay.
Aloha, my name is Jeff James, and I'd like to invite you to watch my show, The Military in Hawaii. It'll be shown every Friday at 11 a.m. here on thinktech.com. Aloha.
Aloha, this is Maria Mera, and I'm here to invite you to my bilingual show, Viva Hawaii on Think Tech Hawaii, every other Monday at 3 p.m. We're here to inform, motivate, and entertain you. Join us. Hola, soy María Mera y estoy aquí para invitaros a mi show bilingüe Viva Hawái en Think Tech Hawái cada 2 lunes a las 3 de la tarde. Estamos aquí para informaros, motivaros y entreteneros. Apuntaros.
Hi, I'm Ethan Allen, host of Likeable Science on Think Tech Hawaii. Come join us every Friday at 2 p.m. when I interview interesting scientists about what they do, why they do it, and why we should all care about it. It's a lot of fun to see. We hear, and you can learn interesting stuff. You'll hear all kinds of fascinating science, and we know you'll have a great time. Hope to see you then. Bye-bye.
University of Hawaii. We're back, we're live, we're here with Patricia Fryer, and we are finding things we never knew before. For example, you know, this stuff is from the Mantle.
Yep.
And I always associated the Mantle with Christmas somehow.
Aha. Well, because of stockings on the mantelpiece?
Stockings on the mantle.
Okay.
Can I borrow this stuff next Christmas? Never mind.
Well, yeah, you know, it wouldn't burn in the fireplace either because it forms at temperatures hotter than any fire you could build.
So this came from deep in the mantle. That means how deep is that?
Well, generally speaking, it depends where you are, but in the oceans it'd be about 8 kilometers down. In the Mariana Trench, it actually is exposed on the seafloor at about 6 kilometers down. And that's great because there are submersibles that can get to 6,500 meters, and I've been in them.
Ooh.
It's exciting.
Ooh. We're going to talk about submersibles. So these were picked up by a submersible then?
This actually wasn't, but rocks like this have been in other parts of the world in other trenches.
Okay, now
But
it's green. You said
that's
that
true.
was olivine?
Olivine, like the green sand beaches on Hawaii.
And what is olivine exactly? Is it a mineral?
Yes, it is. It's an iron magnesium silicate. So it has iron, magnesium, silica, and oxygen.
What does that tell us?
What does that tell us? That tells us that most of the Earth is made out of iron, magnesium, silicon, and oxygen because the mantle makes up the largest portion of the planet.
Now the mantle, you know, it does have the implication just in the language that it's the mantle covering something else.
Yes, the
So
core.
it's covering the core.
Right.
So how deep is the mantle? They had a song by that
Halfway
name,
down.
How deep is my mantle?
Let's see, 2,000 how many kilometers? Exactly, I forget.
But
That's
inside the
embarrassing,
mantle of
yes.
the core. And what is the core made of?
The core is believed to be made of iron and nickel, maybe a little silica, maybe a little sulfur. Nobody's got a piece of it
If
yet.
we had the technology to get in there, into the mantle, we would have an unlimited amount of iron
Well, getting it out would be a trick.
because it's hot.
Oh yeah, it's liquid. The outer core is liquid,
Yeah,
and that's why we have a magnetic field around our planet.
Yeah, because it's all iron in the middle
Yeah, and it's moving,
and it's moving.
right. So that
And-
creates a magnetic field.
And maybe the movement changes from time to
Oh,
time.
definitely, yeah.
And that movement would change what happens in the Mariana Trench.
No,
Oh, okay.
sorry.
It would change earthquakes?
It would change the direction of the magnetic field. In fact, over geologic time, the North and South poles flip. So sometimes the North Pole is the South Pole magnetically.
Wow.
And back and forth, and this does so on timescales. We don't exactly know what the timescales are, but there's a record of it that has been measured on the seafloor that has been set in the rocks that erupt on the seafloor. So the basalts, like typical.
Is that also down in the
No, this actually is from a lava flow, a basalt lava flow that occurred on the mainland, but it looks exactly like the Pahoehoe flows
It does.
on the Big Island, right?
And there's a kind of almost liquid-looking.
Yeah, glassy.
Gouge in it.
Yeah, when the lava cools really fast, the crystals don't get a chance to form, so it just creates a glassy surface on the top of the
I don't know
rock.
if you can see that. If I hold it up.
And get some light on it, yeah.
Yeah, I'm going to hold it up so that you can actually look in that hole there. The puka was shiny inside.
Shiny
It's
glass.
very interesting, yeah.
Right.
That puka there. That is right there. That's so interesting. What is basalt anyway?
Basalt is the typical rock that forms from a slight amount of melting of the mantle. And it is about 50% or so silica, maybe 12% or less magnesium, so iron, magnesium, silica, probably some potassium, sodium, well, not so much potassium, sodium, calcium. Those are the main elements that
So
are
would
in
you
basalt.
find this in the mantle, the basalt?
There's an interesting question. Because the mantle melts in tiny increments that then, because they're less dense, they start to rise up and percolate through the mantle. Yeah, actually you can, but eventually the stuff all kind of gets together and begins to rise through some sort of plumbing system, a conduit of some sort.
Like
That-
lava tubes?
Yeah, or the neck of a volcano. So the conduit of a volcano, comes up and then it
I love
burps
that
out on
term.
the surface.
The neck
Yes,
of a volcano, like a chicken neck.
that's right, that's right.
Twists this way and
Yeah,
that.
it does, actually. Kilauea has a very interesting contorted neck.
You never heard before. Now you're hearing about the neck of Kilauea. So, okay, now this is another rock, but this
Yeah.
is based on the olivine.
Yeah.
Because something happened to the olivine.
Yeah.
It got involved with what?
Water.
Water.
Yes, this is a piece of the mantle too, but it has been hydrated. It has mixed with water chemically, and basically it's the same composition as the olivine. We call the main rock that forms the mantle peridotite, and it's just olivine and a few other minerals, pyroxene, and it can alter as water moves through it and combines with the original minerals into this green, sort of greasy looking, I don't know if you can see
We can
that,
see that, yeah.
the shiny, greasy surface. This is very typical of serpentine, and this generally will form wherever fluids are coming off the downgoing, the subducting plate. So as in the Mariana system, there are lots and lots of faults in the plate that's not being subducted, overriding the Pacific plate as it goes down. And
Subducted means the one going down.
subducted means the one going down, so the downgoing plate is going into hotter and greater pressure areas in the mantle, and initially it starts sweating out fluid from the sediments that are going down, and the rocks beneath that get squeezed, and basically it's a distillation process. You've got a giant still down there that's releasing fluid that comes up through the faults, and it can form these kinds of alteration products.
But it's heat. Heat is the operative thing here.
Water
Just
is the
pouring
operative
water on it's not going to do that, is it?
Actually, you can form serpentine in your backyard
Is that right, without heat?
without heat. Well,
So-
without not much heat.
It has to stay there for a while? And
Yes, yes.
What, long time. So it's a long time with it.
Yeah,
The elements combine with each other. And all that.
right. But you're right, in the Mariana region and at depth, where it is warmer, the reaction goes faster.
Okay, so many things to talk about, but you
I
know.
know.
First
come
is
back tomorrow.
I like to stop at this point and
Okay.
ask you, Patricia, how do you know this stuff? I mean, it's hot down there.
It is hot
How do
down
you
there.
get there and observe this and be able to
Oh.
tell us about all these chemical, processes that are happening, transformations of rock? How do you know?
Well, the wonder of the Mariana region is that it just brings it right up to the surface for us. Because there are all these faults down there, and the rocks are grinding up against one another, they break up at the fault zone, and then when the fluids escape and come up the fault zone, they remobilize all that mush, and it is lighter than the stuff around it, so it comes up and squirts out on the seafloor and makes mud volcanoes. And those mud volcanoes bring up pieces of the mantle. They also bring up pieces of the top of the downgoing plate. So we can look at the minerals that are in the rocks that it brings up, and using techniques that tell us what temperature and pressure conditions certain minerals are stable at, we can backtrack and figure out what the temperatures and
From the
pressures
rocks.
were from
But
the
you got to
minerals
get the
in the
rocks, and you get the rocks
Get the rocks,
through these
mud volcanoes,
mud volcanoes.
squirting up pieces of the downgoing plate and pieces of the mantle, and it's just great.
Okay, so no, if you're making notes, you probably want to include a short glossary of subduction.
Subduction,
Okay,
Downgoing
mud
plate.
volcanoes.
mud volcanoes,
That's- down deep.
squirting up pieces of deeper stuff onto the seafloor.
It takes what, hundreds, thousands of years, but
Millions.
millions of years.
These have been doing it for 50 million years.
Squirting may not be, you know,
No,
the
it's
right
more,
connotation.
It's oozing, yeah, oozing.
Okay, then you get chicken. This happens.
Yep.
And then, and this is the telltale, you get mush.
You get mush. You get mush, and also you get springs, you know, where the fluid is coming out. And this reaction to serpentine is particularly cool for microbes because it releases hydrogen. And hydrogen is something that they need for their metabolism. So we get microbial communities, and then they feed critters that live on the seafloor. So we get mussels and clams and little
interesting.
worm tubes
Yes.
and crabs and all kinds of weird things,
Yes.
which I don't really know all that much about, but they're fun to look at.
So the microbes are on the rocks or
They're
near the
in
rocks?
the
In the rocks.
They're in the mud.
In the volcanic,
In the
the-
serpentine mud.
the mush.
The mush. Yeah.
Serpentine, what is serpent, what does that mean?
Serpentine
is a
is-
serpent involved here?
Yes, because it's green, so it looks like a serpent.
Okay.
So that's where it came from, the term. Serpentine is probably best known to people as an asbestos mineral. So don't worry about this one. I mean,
Okay.
it's perfectly safe.
Now you have another big rock
Another
over there.
thing, yes.
The thing, this is really the category killer. You know, let's wait.
Okay.
We're gonna come back.
Okay.
Okay, this, if you thought the last one was a cliffhanger, this is a mountain cliffhanger.
Oh,
This is really
yes.
an Everest kind of cliffhanger.
This is the
We come back,
savior
you'll
of the
see
world.
this amazing gizmo. We come back.
Okay.
We'll be right back.
Aloha, namaskar, and hello. My name is Anu Hittel, and I host a show, Climate Change Beyond Outrage. In it, we go beyond outrage to look at solutions to climate problems facing people, nations, and the world. Join me every Tuesday at 1 o'clock Hawaii Standard Time. See you then.
Aloha, my name is Richard Emery, and I host Condo Insider. We talk about issues facing the Condo Association throughout Hawaii and talk about solutions. When you think about it, about 1/3 of our population lives in some form of common interest real estate. We broadcast every Thursday at 3 p.m. Please tune in, and thank you. Aloha.
Aloha, I'm Kaui Lucas, host of Hawaii is My Mainland, here on Think Tech Hawaii every Friday at 3 p.m. We address issues of importance for those of us who live here on the most isolated landmass on the planet. Please come join me Fridays at 3 p.m.
One of the
a little one.
volcanoes, yeah.
Okay, we're back, we're live, and we're still holding back on the big thing, the mountain cliffhanger.
Okay.
Huge, big cliffhanger. But something came up, you know. See, it happened again. There you go again. You weren't listening during the break. During the break, we were talking about Blue Mush.
Yes.
It's like Blue Planet, Blue Blue Foundation, Blue
All right.
Startups. This is Blue Mush.
Blue mud.
Wait till they hear about this. Now, this is, you put some, PVC down into the bottom of the,
Yes, we line a metal tube
Yeah.
with a PVC pipe
Yeah.
and put it like a 1-ton weight on the top of it.
Yeah,
And we
and
have
drive it down.
Yeah, we have it on a cable. We lower it down close to the seafloor, and then we let it go, and it goes crashing into the seafloor and goes.
like a spear.
Yeah, like a spear, a hollow spear, and
Okay.
it makes a core, so it brings it back up, and then we take the PVC pipe out of the metal pipe, and then we cut it in half and open it up, and by gum, this stuff, serpentine, looks like that shirt you're wearing.
Okay, Blue Mush.
Blue mud. It's
Mud,
wonderful.
mush,
wonderful.
mud,
We
mud.
call it mush. Yeah, it's
Yeah.
not really too
and
mushy.
it's mush. I mean, you can actually
Some of
manipulate
it you can. Oh yeah, it's a little bit stiffer the deeper you go.
Mm-hmm.
You know, And it's kind of like silly putty. You know, if you whack on it, it's kind of hard, but if you push like a little sample tube into it, you can get it in there. But it's the color of your shirt. It's just really a surprise
And now
when we first
the
got it.
big question.
Yeah, why?
We haven't gotten to the cliffhanger yet,
Yeah,
but
okay.
now the big question. Pourquoi bleu?
Pourquoi bleu? Because of the microbes. There are microbes living in the mud because this reaction gives off hydrogen and other things that they love to eat. And they live in an environment that has no oxygen in it. And because of that, they exude sulfur and methane and things. And because it's an anoxic, non-oxygen environment,
okay.
it looks, you know, like the black stinky mud that
Yeah.
you see
Would it be
at the bottom of the
dangerous to touch
island.
it? Dangerous?
No, you can touch it.
You have?
I'll bring you some next time.
Yeah. Okay, next time.
Okay, blue mud.
We're recording this
All
now,
right,
yeah.
that's a promise.
All right, so let's go to our second cliffhanger, major cliffhanger you have.
Ah.
What do you got over there in the ditty bag over there?
I have something that will save the world from us.
Okay, this is a big deal.
Okay, this is a big deal. This is a big thing, too. This is very bright. This is a carbonate chimney. This is made out of calcium carbonate, the same thing that forms seashells and coral reefs. It forms, though, on the top of these big mud volcanoes because the fluids that are coming off the downgoing plate have a lot of carbon dioxide dissolved in them. When the carbon dioxide exits the seafloor at the top of seeps on top of these mud volcanoes, it begins to react with seawater and crystallizes in these weird, wonderful forms. So it was
It
kind
would
of...
be in this direction, too.
Yes.
It would be vertical this
It was
way.
kind of stuck in a crack right about here where my hand is, and then it grew up this way. And what helps it to grow, actually, is the microbes that live in the mud down below.
Was it blue before?
No. This is always white.
Okay.
But
Calcium carbonate chimney.
chimney, right?
Okay.
Yep.
Okay.
People may have heard of black smokers. They form chimneys too, but those chimneys are made of metal sulfides, a variety of other precious metals. But these form under cooler conditions, so lower temperature seeps, and an interaction between these carbon dioxide infused fluids. So the reason that they're forming is because they've come through this serpentine mud stuff and exited the seafloor. The process by which this reaction takes place is taking place in nature. It's something that people are talking about trying to do on land to capture carbon dioxide from the atmosphere and fight against global warming. So nature is doing it already for us. If we could learn more about
How is nature doing it?
through this very process of
What is that, though? I mean, so you have certain things coming up through the, okay, and there's carbon in there.
Yep.
And
Carbon dioxide.
Carbon dioxide is in there.
in the
and
fluids.
what's the chemical reaction that actually draws that into the
calcium is-
calcium carbonate?
Yeah, the calcium is coming from seawater, and the carbonate itself is coming out of the fluids. So as long as the chimney is active and the fluids keep moving up it, it can continue to grow and exist on the seafloor. It's so cold down there that if the fluids weren't active, this thing would dissolve away because calcium carbonate will dissolve in cold seawater.
But it doesn't.
Okay, and
it
well,
makes it into a hard,
Yep,
and they get, oh yeah, can I?
sure.
Oh, yeah.
It's a bit heavy.
It's not that heavy. It's not
No,
really like rock.
No, it's quite porous inside
Yeah.
to let the fluids move through it.
So, is this an average size chimney, or do they come bigger or smaller?
Both. They come huge. There are some that are about 30 feet tall. that have giant pieces that have littered the seafloor around them. So obviously if there's an earthquake and the thing is shaking, it might break off, but then it will grow again. So I've seen, they look like a saguaro cactus, kind of, you know, with kind of a weird arm sticking out the side.
Perfect.
So they can grow huge, and they can grow over very long periods of time, like thousands of years.
How long does this one take to grow, do you think?
That's a good question, and I don't know the answer to that, Jay. We're just starting to date this. I have a colleague who's visiting from China, and she is able actually to date these, and she came up with some preliminary dates on another one of these that was as old as 11,000 years. So the youngest date we've ever got from one of these is about 180 years, but that was a fairly large chimney like this.
So if we could figure out a way to emulate the natural process here,
Yeah.
and what is it, bond up carbon into this kind of stalagmite thing, then we could lock the carbon in structures like this.
Sure, sure.
And then it's not active, then it's not screwing up our environment.
That's
it's
right.
not screwing up our chemistry and all that.
Yeah, that's right.
So all we need to do, should you decide to accept the mission, is find a way to emulate that, what,
Yeah.
on land?
Yes. Actually, I have a friend, Peter Kellerman, who actually is working on that right now. And he is interested in looking at ways to pump warm, carbon-enriched fluids, like, you know, just carbonated water, into material from the mantle that's exposed on the surface of the Earth. And that will bind calcium carbonate into the material that's exposed on the surface of the Earth. The thing that's important about trying to understand how nature does it is, you know, man, she's been doing it for 50 million years for free. You know, it takes a tremendous amount of energy and know-how and equipment and money to be able to do this ourselves. But if we can figure out how to do it the most efficiently possible, then of course that's a benefit to mankind.
That would be fabulous.
Yeah.
What would you do with the stalagmites? I mean, like chimneys. What would you do with them now that, if you have achieved this success in bonding the carbon to the rock chemicals?
Well, you know,
what would you do with that stuff?
what would you do with the material afterward? Well, it would just kind of sit there, but
Doesn't have to go anywhere because
Doesn't have to
it's
go anywhere.
inert.
yeah, right.
Yeah.
The thing I think that would be important about this is because we know these chimneys and others around the world that form in association with mantle rocks exposed on the seafloor, is that they're associated with biological processes too. Maybe that's the clue. Maybe something completely outside my field is important for understanding how to do this the natural way, you know, the way nature does it, and involve microbes in the process.
Dave Carl comes to mind.
Oh yeah, Dave definitely comes to mind.
Seymour,
Yep.
the Center for Macrobial Oceanography Research
Yep.
and Education. Whoa,
Yeah,
that would be
that's
something.
right.
Bring them together.
Oh,
Okay,
yeah.
we have a few minutes left.
Okay.
And I want to talk about the Pisces. I want to talk about how you go down there.
Okay.
You said you have been down there.
Right.
Was it 6,500 meters, you
Yeah,
said?
almost.
Almost, okay.
64.99.
That's close enough for my money. So what's it like, actually?
Oh
Pat?
gosh, it's wonderful. It's exciting, and it's descending through the darkness. You look out the portholes, and usually the pilots haven't turned the lights on yet because it's battery powered and we want to save the batteries, right?
Yeah.
But there are jellies and foraminifera, these little one-celled guys that show phosphorescence, you know, and
Jules Verne,
oh, it's like going through
20,000 leagues under the sea.
Absolutely. It's like going through a fireworks display. A lot of these animals have cilia, these little arms, you know, when they're moving, each one of them shows a different color. As it goes around the body of the creature, it's just, chicken skin, you know, it's just so cool. And then as you get closer to the seafloor, the pilots slow down the descent, right? and they start turning on the lights, and about 30 meters, so 90 or so feet above the seafloor, you're looking out the windows. And usually the scientist is lower down than the pilot, so usually we get to say, in sight first before they see it, and then you settle down on this, whatever it is. And whatever it is, nobody has ever seen it before.
You scared?
And that is the coolest. I'm too excited to be scared. I should be scared. It's really stupid to do this, but if you've ever seen one of my favorite movies, which is the Russian water tentacle movie, The Abyss, you would see what would happen if anything were to go wrong with the submersible, and it would be quick. So at least it would be quick.
You wouldn't know what was going on,
You would
and you'd
feel
be
things.
pulverized.
Just
That's it. Now, why does it? You mentioned the word movie, and this fantastic thing that I discovered about you just a minute before the show about advising James Cameron,
Yeah.
the movie man. What was that
God.
like?
Oh, it was a trip.
Literally.
It was the most unusual research expedition I've ever been on, I have to say that. But the coolest thing about it really was that I was so surprised that this man, genius with movies that he is also a total geek. He is an engineer. He knew every component of that submersible that was designed. He helped design it. He understood every piece of it, every mechanism. And when I first met him, I thought, oh boy, I've been approached by people who wanted to put radioactive stuff in the trench because it'll go down, it'll never come up.
No.
And I thought he was going to kill himself. So I made 62 questions I was going to ask him, and met him for dinner and started on the list. And about question number 5 or 6, I realized I was talking to a colleague. He knew what he was doing. He's an amazing character. And the expedition itself, all of the people that he had amassed had specialties in engineering or electronics or whatever, but they also were the film crew. And so, they're doing 2 jobs all day long, high energy environment, and phenomenal expertise.
So what kinds of things did you advise him about?
He wanted to know where to go in the trench to go to, the deepest spot. We had, I had been on the expeditions from the University of Hawaii.
Oh, you knew the trench.
And we'd mapped the trench very carefully. What it turns out is that mapping it with sound is deceptive because the sound signals can penetrate very, very soft sediment. And so some other people who had mapped the trench had found deeper spots over a little further to the west, but actually those were...
There's the trench.
Oh, there's the trench.
I didn't realize it was so brightly colored.
Well, it is.
I'm only kidding.
If you want it to be.
Thank you.
So when you map it with sonar, with sound, the sound can penetrate this gooey, just really soupy sediment and go down a little bit. So we had actually taken the Woods Hole Oceanographic Institution's robotic vehicle, the Nereus, to where Jim wanted to dive in 2009. So Jim went in 2012, and I had the map, so I picked the deepest spot on the map, and that's where he put down.
That's the deepest spot. We know that is, the deepest spot is, what is it called? Wait, Challenger Deep.
Challenger
That's
Deep.
the deepest spot in the trench. How deep is that?
It's, well, the measurement that we got was 10,924 meters. So that's deeper than Everest is high.
Wow.
You could turn Everest upside down into the trench, never see it again.
What was the movie now? Did I see it? I didn't see it.
Which movie?
The one that he made based on all this.
Oh, he made Avatar most recently. He's working on Avatar 2, which will be set in the world that he created is named Pandora. And the number 2 movie will be in the oceans. And I'm hoping he's going to say something about trenches.
I hope he says something about you.
Oh, I doubt it.
So one last question, just
Sure.
curiosity. Why don't we drop our nuclear waste at the bottom of the Challenger Deep?
Oh, well, like I told you, what goes down often comes right back up.
There you have it. Patricia Fryer, Hawaii Institute of Geophysics and Planetology. We're talking about research in Manoa. We're talking about subduction, can be fun. Can be a beautiful thing.
And very interesting.
And fun. And remember this, what goes down ultimately will come up.
Yeah.
You heard it on Think Tech. Thank you so much, Patricia.
Oh, thank you, Jay. Good to talk with you.